Darjeeling Learning Hub welcomes you all for this new episode. This episode is in the PG level. So this is the first video that we are going to upload it. And here what we are going to study here is the reduction of two body problem into one body problem. First and foremost, we have to understand what is meant by a two body problem. Why we have to reduce it to one body problem. There are plenty of examples. First one is the earth is revolving with the sun is one of its forces. This is one of the two body problem. Or you can think it of a moon revolving around the earth, and this is also another two body problem. And also you can think it of an electron revolving in elliptical orbits in the nucleus, around the nucleus. So this is a two body problem. That means one body is in motion under the influence of the force field created by another body. So these two bodies are interacting with one another, and because of that an interaction potential is developed. In that force field created, the particle or the body is in motion. So this is a complicated problem. We take a lot of difficulties in solving the problem. Therefore, we would like to reduce it as a one body problem. So this chapter deals about the reduction of a two body problem into one body problem. And by solving this, we are going to find out the position of the body at a particular time. What would be the position of the body at a particular time? You can think it of the moon or the earth or the sun. In which direction or in which angle the sun will rise, or in what day the moon will be a full moon day. So all these things could have been explained by this reduction of a two body problem into one body problem. Though the strategy that we are going to follow here is, first and foremost we have to form the Lagrangian for one body problem. Then we have to write down the equations of motion for that body. Then we have to solve the equations of motion, and we have to find out the position of the body at a particular time. So these are the four stages by which we are going to follow. First one is the reduction into one body problem. Second one, we have to form the Lagrangian. Then we have to write down the equations of motion. Finally, we have to solve the equations of motion and find out the position of the body at a particular time. So for that you consider a monogenic system of two mass points. First and foremost, you have to understand what is meant by a monogenic system. As I had already told, the body is in motion in the interaction potential developed by the two bodies. So the only forces are due to an interaction potential V. And for this two body problem, let us imagine, you see this figure, we have two bodies of mass M1 and M2. And the two bodies' masses will be concentrated at a particular point, and that point we call it to be the center of mass. The position of the mass with respect to the coordinate system is capital R, and the two bodies are at a distance R1 and R2, and the difference vector R will be equal to R2 minus R1. Therefore now here we have 6 independent generalized coordinate to represent the position of the body. How? That means for the center of mass we should have 3 coordinates, and for the difference vector small r we should have 3 component vectors. So altogether we should have 6 independent generalized coordinates. And now here this Lagrangian could be written as L will be equal to, that is given by equation number 1, where kinetic energy is a function of capital R dot and small r dot, and the potential V is also a function of small r and small r dot. Now the first, if you take the first term alone, the kinetic energy term, the kinetic energy is due to the sum of the motion of the center of mass, and it is the kinetic energy of motion about the center of mass. Therefore, two kinetic energies has to be added. One, the center of mass itself is in motion, and because of that you should have a kinetic energy, and with respect to the center of mass the two bodies are in motion, and that kinetic energy has to be added. Therefore, the total kinetic energy is given by equation number 2. First term represents the kinetic energy due to the center of mass, and the term T dash represents the center of mass due to the two bodies moving under the point center of mass, and that is given by equation number 3. Now we have one term R1 and R2. What is R1 and R2? R1 is the radius vectors of the first body from the center of mass, and R2 is the position vector of the body 2 with respect to the center of mass, and that is given by equation number 4. Now square the equation number 4, substitute in equation number 3, you will get a T dash will be equal to 1 by 2 m1 m2 divided by m1 plus m2 into r dot square. So that is the kinetic energy due to the center of mass, the motion about the center of mass. Now this is T dash. So substitute this T dash in equation number 2, and then once again both in equation number 1. So what will you get here is the first term could be neglected, substituting this in equation number 2 and dropping the first term, so that the center of mass is at rest or moving uniformly. So we consider the center of mass is at rest or moving uniformly. That's why we are neglecting the first term, and you are getting this equation number 5, where the portion 1 by 2 m1 m2 divided by m1 plus m2 is called the reduced mass, and it is represented by mu. Therefore, the Lagrangian is L will be equal to 1 by 2 mu r dot square minus V of r, and the mu is called the reduced mass. Now the reduced mass is in motion with respect to the distance r. Therefore, now the two body problem is converted into one body having the mass mu, and the mu value is given in the side as m1 m2 divided by m1 plus m2. So now we have reduced the two body problem into one body problem. Now we can solve the equation. Therefore, now here the procedure we have known. Now let us go to a special case here. Now so we have a single body problem, that means one body problem, which has the reduced mass m, moving in the conservative central force where the potential is only a function of r only. Now the problem has a spherical symmetry, that's why we have the angular momentum L vector will be equal to r cross p. It is conserved. That means the central force motion will be confined to a particular plane only. The motion of the single particle in space could be described in spherical polar coordinates theta, phi and r. Choose the polar axis along the direction of L. If you choose the direction along the L, then motion will be in a plane perpendicular to L. And now here the Lagrangian for this case should be written as L will be equal to T minus V, that is given by equation number 1. In spherical polar coordinates we have written this equation. And moreover, since theta is cyclic coordinate, the corresponding canonical momentum could be written in terms of the angular momentum of the system. That is, P theta must be equal to dou L by dou theta dot. Therefore, you derive this equation, differentiate the equation of 1 with respect to theta dot term. That will give you the canonical momentum. Therefore, when you differentiate the equation number 1 with respect to theta dot, you get mr square theta dot. Now, we can easily go for the first integral, or we can easily write down the equation of motion. We know the equation of motion, Lagrange's equation of motion given here. d by dt of dou L by dou Qj dot minus dou L by dou Qj equal to 0. So this is the Lagrangian equation of motion. Now here the first generalized coordinate is theta. Therefore, we can write down the first equation of motion in terms of theta. Here, if you see that equation, the Lagrangian equation, there is no term involving theta, but we have the term only theta dot alone. Therefore, the first in the Lagrangian equation, second term will be equal to 0 because theta term is not there. So only the first portion d by dt of dou L by dou Qj dot alone is there. Therefore, p theta dot must be given by d by dt of dou L by dou theta dot, and that is given by equation number 2. Dou L by dou theta dot, in the previous slide we calculated it to be m r square theta dot. Therefore, differentiation of a quantity inside the bracket is equal to 0. Differentiation of a quantity inside the bracket is equal to 0. That quantity must be a constant quantity. Differentiation of a constant should be equal to 0. Therefore, m r square theta dot should be a constant, and that constant is called the magnitude of the angular momentum, and that is given by the letter L. So from 2 we come to the conclusion that the angular momentum is conserved, and that is the first integral. Angular momentum of a two-body problem, when reduced to one-body problem, it remains constant. Now we can go further from equation number 2, d by dt of m r square theta dot equal to 0. Now this could be written as 1 by 2 r square theta dot will also be equal to 0. 1 by 2 we have added, because 1 by 2, when you add this, that will give you the aerial velocity. That's why we have added, because it's a constant quantity. So we have added a constant 1 by 2. So differentiation of 1 by 2 r square theta dot should be equal to 0. That means 1 by 2 r square theta dot must be a constant quantity. And that constant quantity is called the area. So previously we proved that angular momentum is constant. Now this angular momentum we calculated in another way, that will be equal to the area. How it is the area? You see the figure here. In the figure you are having the area. We can calculate that area, that conical section, by the radius vector. The radius vector sweeps an angle d theta. So that area is of r square theta dot. How? That area will be equal to, we can find out the arc will be equal to r d theta. How? D theta equal to arc divided by radius. That is the trigonometric formula. D theta will be equal to arc divided by radius. Therefore, arc will be equal to d theta into radius, that is r d theta. Now we have to find out that area. To find out that area, having r d theta in one side and r on the other side, if you multiply it, you will get the area of the rectangle. But this is half of the rectangle, that's why 1 by 2 r into r d theta. So that is the area. Now differentiate these equations. Therefore, dA by dt, d theta could be written as d theta by dt. dA by dt will be equal to 1 by 2 r square d theta by dt. This is what we have already found out. Theta dot. Theta dot could be written as d theta by dt. Therefore, this is also a constant quantity, because we proved d by dt of 1 by 2 r square theta dot will be equal to 0. Therefore, that aerial velocity 1 by 2 r theta dot is the aerial velocity. That is it is the area swept by the radius vector per unit time. That is also constant. This is the Kepler's second law. According to the Kepler's second law, the radius vector sweeps out equal area in equal interval of time. Therefore, from the first integral, we come to the conclusion of two aspects. One is the angular momentum is conserved. Second one is we have proved the Kepler's second law also. Now let us go to the another equation of motion in terms of r. So in terms of the first coordinate theta, we have written that equation. In terms of r, we can write down this equation. That is, you see in the corner, we have this L will be equal to T minus V. Find out dou L by dou R dot, that is Mr dot. Dou L by dou R equal to Mr theta dot square. Substitute these two in the Lagrangian equation, we get equation number 1. So now here, in equation number 1, instead of second term Mr theta dot square, you see above my head, that is another portion is there, that is theta dot will be equal to L by Mr square. From the previous slide we have taken it and substitute it. Now take this 2 to the other term, other side. So we are getting this one. Therefore Mr double dot will be equal to minus d by dr of the term inside the bracket, that is V plus 1 by 2 L square divided by Mr square. Now multiply both sides by r dot. When you multiply by r dot, you are getting the next term. Now this term could be written as d by dt of 1 by 2 Mr dot square will be equal to minus d by dt of the term inside the bracket. So that d by dr has been changed to d by dt by the multiplication of r dot. Now bring it to one side, because everything on the left hand side and the right hand side are the differentiation with respect to time. So we can club together. Therefore d by dt of the term inside the bracket must be equal to 0. Therefore the term inside the bracket should be equal to a constant, and that is called the total energy. First portion is the kinetic energy, second portion is the interaction kinetic energy, and the third one is the potential. Therefore total energy remains constant, energy is conserved. Therefore what are the things that we have proved by the motion is, we proved that angular momentum is conserved, we proved that the energy is conserved, and also we proved that the Kepler's second law also. Now we can find out the position of the body, that is theta of t and r of t. So from the previous slide we have that equation which I had written above. Therefore 1 by 2 Mr dot square will be equal to E minus V minus 1 by 2 L square divided by Mr square. From there you can find out r dot. Then from there you can find out dt. When you integrate this you will get t. That means we found out the time as a function of r. So if we invert it, we can get r as the function of t. So from the equation we can find out the position of the body in the two body problem. Similarly we can find out the angle of the, locate the position of the body, locate the position theta also in the portion that I had given in the corner, that is Mr square theta dot will be equal to L. From there when you integrate you will get theta will be equal to that equation written here. Therefore theta could be found out from that integral. Therefore in short we can locate the position of the body r of t and theta of t from these two equations. In this manner one could solve the two body problem into one body problem. So my dear viewers, I hope this would have been very useful to you. You would have enjoyed, I hope. Thank you.
இந்த வீடியோ உங்களுக்கு பிடிச்சிருந்ததுன்னா லைக் பண்ணுங்க, ஷேர் பண்ணுங்க, கமெண்ட் பண்ணுங்க. இதே மாதிரி இன்னும் நிறைய வீடியோஸ் பார்க்கணும்னா மறக்காம டார்ஜில் லேர்னிங் ஹப்பை சப்ஸ்கிரைப் பண்ணுங்க, அந்த பெல் ஐகானையும் பிரஸ் பண்ணுங்க.